Our next speaker, this is Alexander Fritzler, the senior developer at Multicento Yandex Search. And Alexander is going to tell us about how they are managing the short-sightedness of recommendatory systems. Ivan, hello. Thank you. I work at Multicento, and we're developing the recommender platforms that are facilitating recommendations to various Yandex services. The plan of my presentation is the following. First, I'll tell you about the service we're going to discuss today, traditional ranking methods, further the long-term matrices for the methods, and a little bit about RL in general, about our initial approaches, what happened, and at the end, some future plans. So, let me tell you about our service. We are going to talk about music recommendations, especially using the Alisa AI for Yandex. So if you say, Alisa, turn on the music, our platform turns on. Or if you ask Alisa to go to a certain track, the track ends, and then a recommender flow from our platform is connected. A few other scenarios are also available. Now, this is the global overview of the structure. We have a request from the user with some features. Then, using our database of millions of tracks, we select a few thousand candidates, rank them using ML, and serve top to the user. In our case, this is the top 5 tracks. This is done to save computational capacity and not to overload the system, make it redundant. We use CatBoost machine learning model, and using this model, we are predicting the possibility of positive feedback from the user to a certain track. So if the user likes the track, he listens to the end of the track, and negative feedback is dislike, skip, and so on, other negative emotions or actions that are expressed. Now, what are the side effects of this approach? First of all, music is quite specific in a way that is quite easy to receive positive feedback. All you need to do is show the track that he has previously liked. On the other hand, if you do it continuously, then despite the fact we will get positive feedback, we will lose long term, because the user will lose interest in our recommendations and in the service. Of course, we'd like to avoid that as much as possible. And with that view, my colleagues from Sber team have developed an alternative model called discovery model. We won't go into the workings of the model now, but it provides for generation of new recommendations using different models at different times. And behavior has long-term implications. We also saw that the matrices are falling, and we saw that in most cases the users are fine with listening to previously listened tracks. They're fine with the tracks they previously liked, and we need to turn on this discovery model only so often. And probably on some of the features it is possible to predict when it's worth connecting the discovery model. Also, the long-term effect is quite interesting. You are using the discovery model, and the search query is showing a drop. So, for example, a user skipped more tracks than usual, but the fact that we sometimes connect the discovery model long-term will increase user retention and user involvement into the service, and we'll try to predict that, to learn and predict that. Now, to the long-term matrices. The main metric is the total time user spends on the service scenario. This matrix is called time spent. The happier the user is, the more time they spend. Also, we are looking at other time spent in other scenarios. This may be general total recommendations, or if the user is asking for a specific track, then we have recommendations on the track. It's called radio on track radio. And also we are interested in the amount of positive and negative feedback, likes, dislikes, etc. And also retention of users to the app or to the scenario is important in a week's time, in a day's time, and so on. It is quite difficult to change it in a statistically significant test. trial. However, it is worth noting there is a sphere of machine learning where we make decisions while trying to maximize the long-term sum of rewards. This is called reinforcement learning. On this slide now, you're able to see the screenshots from the most popular case of using RL. This is Atari, the famous Atari game. Music and gaming actually does have many parallels. I'll go into that a bit further. Now, moving on to the RL tasks. In RL agents, we maximize the total discounted reward. So, on the slide, you see the formula. R signifies the reward, and also gamma parameter means the long term, the period of looking forward when summing the rewards. 0 to 1 are the values for gamma, where 0 is the current reward. Now, why do we need this discounting? If we don't have it, theoretically, we may have this endless future time spent. And this is certainly non-preferable, because endless targets are bad, and we won't have a time, we won't be able to wait for the moment to count that, so we'd like to do the discounting. And also, the more long-term metrics we used, the closer gamma is to 1, the harder is the prediction of this total sum reward. And accordingly, the impact of the reward is falling depending on the current action. So the task, the job, becomes more noisy and complicated. We decided to discount twice every 2 hours, as opposed to normal RL. It's not discrete but real time, so we are discounting based on real time as well. So our approach and result was the following. In RL, at each step, we maximize the discounted time spent. Also, the state of environment, what we are using for decision-making, are the user's features, and the state of actions is the choice of 2 recommendation models. So, only 2 questions remain. How can we build a data set, and how can we train a model? Now, let us begin with a simple. The data set. First, we need to generate data by random use of the discovery model with a small probability. So, a certain formula with a general recommendation model or a discovery model. It cost us a small drop in time spent, however, we needed to start with something. Further, we endlessly iterate 2 things. First, we train the model using the data we collected, and then we move the model to production, collect new data, and this is the online learning process with these long iterations. It can be repeated endlessly. Now, to the methods. I will try to be very brief as to the types of methods. RL uses many algorithms, but we are interested in specific division. This is the off-policy and on-policy method. Speaking of policy, RL says that there is an ideal optimal strategy, ideally representing this discounted sum total reward, and this strategy is marked as P with an asterisk. Accordingly, we may calculate the mathematical expectation of the time user total discounted time spent at a condition that we are now currently in S, will perform action A and will then play using the optimal strategy. If we do, this is also called the optimal call function. If we can learn such a call function, then based on this function, we can take optimal decisions in the environment. Using this function at any given moment in time for all possible actions. Here we only have two, and select optimal. Now, RL theory fortunately says that call function can be learned. And also, we don't need to take this optimal strategy from anywhere, so we're able to learn this call function by playing through another strategy. Theoretically, that's the way it should work. Now, as opposed to this approach, there is a non-policy approach, where we don't have this optimal strategy and only the current strategy, just called P. And accordingly, for the P strategy, we are also able to educate to learn a P function, which will depend on the expected time spent action, also considering the fact that we'll continue playing the strategy in the future. And that's the difference between the two approaches. Usually the applications or the articles use off policy, since this method can provide optimal call functions. So we tried that initially. We used the learning algorithm, Q-learning algorithms, for this call function learning. It has many other funny names. So, our job was using data sets to train the optimal model. After we did that, we were able to train the call function to a decent, acceptable standard, and once we moved it to production, it turned out that the total music user time spent grew by 1% and feedback increased by 15%. Certainly 1% total time spent, 1% growth is quite a lot, since music recommendations exist for many years, and every growth by 1% is quite serious work. So this success presented within the framework of these specific algorithms is quite an achievement. Also, feedback increase amounted to 15%, not only likes, but all types of feedback, and the more feedback we generate, the better it is, because we can provide for better quality learning using our data sets. After we moved it to production, it became unclear how can we use it in online. Usually, simulator, we only monitored the rewards. And here, every test is an online experiment. Certainly, we cannot change the hyperparameters and institute local improvements. We are not able to train and test every model online for a week or two. So no matter how hard we tried, we weren't able to resolve the problem, and we tried using a different method class called onPolicy. The algorithm name is unclear here. We called it policy valuation. So we learned the call function to use the current strategy. And accordingly, we were able to improve the current strategy by selecting the actions recommended by the call function that we learned. So we improve the P strategy by the QP function, and we can endlessly improve our model using this. Now, there are great advantages. We can use offline validation because we're using the current strategy, trying to predict discounted time spent. But because this strategy exists in real time, we can use it for regress analysis. We can do the squares, compare models. That's a great advantage. And also the cons include that we are able to do policy improvement iterations once a day or twice a day. Actually, in real articles, we see thousands and millions of iterations. Certainly, it's very little in comparison. However, we may only shrug our shoulders and hope for the best. When we first launched the model, it turned out to be more efficient than the previous. We had improved improved the recommended time spent by another 1% compared to previous slide. And it would have seemed that the difference to the previous model was not so extensive. But the fact that we were able to validate the model offline was a serious advantage. And finally, that's the model we selected for that very reason. This fact of offline validation is vital for us. Now, we also tested an alternative approach, training a queue function for direct track selection, where our actions are the actual tracks. There was a problem here related because tracks are delivered in top 5. We only deliver top 5 out of the rankings. And otherwise, it may be very difficult to calculate the maximum of the function. That's why it wouldn't be completely fair. So the trajectories became 5 times longer because there were 5 times more tracks compared to queries. And accordingly, the environment, the space, action space grew, increased. On the one hand, provided more flexibility and freedom and more complexity also on the other hand. So the job was quite complex, however, the function was learned. Now, let me tell you more about the implementation. Initial model used a predicting model, giving scores for certain tracks, so probability of positive feedback. And here we predict not just the probability of feedback, but directly long-term time spent using the current track. So we are able to score and mix, and then sort this weight results. This weight that the model, RL model, uses is boosted from 0 to another number close to 1. We do it gradually because it is safer. We can observe if the algorithm still stands true with gradual increase. However, we increase the weight quickly from 0 to 1, the feature dispersion will be fast and some instability is still possible. So that's the reason for gradual progression. We haven't gotten it to 1 yet. We're halfway. I'm sorry, we are limited in terms of time. We only have 1 minute remaining. Thank you. I'm in my last slide. So this algorithm provided plus 1% on recommended time spent and a 10% decrease in feedback. Well, right now we are trying to resolve this problem by implementing the new model that optimizes the long-term feedback, and accordingly results are still in project stage. We're still working on it, and that's all for me. Thank you. Thank you very much. It's quite interesting. Unfortunately, we have stepped outside the schedule.